Yeah, so it's the last talk of the day. So I thought, okay, let's start with like the kind of waking sign of like what's happening with the neural nets. And then I listened to the Shirley's talk, and then I was like, that was a really provocative question at the end. So can these deep learning models discover some kind of new physical law? And then I realized that actually, in some sense, all these machine learning algorithms are supposed to do so, because otherwise, how would it actually solve the problem to start with? But today I'm going to focus on the natural language side, on how to use this kind of neural net to discover the structures behind some kind of sequential data we have. So at the end of the day, a lot of problems in natural language processing, or the more like the generation, can be framed into a simple structured output prediction problem. So the input is going to be some kind of high dimensional object, and the output, again, this time is going to be a very high dimensional object. And then output dimensions are highly dependent on each other, and then we cannot really factorize the distribution over the output given the input. So we cannot really determine the pixel value of each and every output without deciding which values we are going to assign to other pixels. It's often really difficult, even if we can train this kind of model to score all possible outputs, because there are often exponentially many possible configurations, or sometimes factorial if you are looking at the ordering of all those different things. The one problem that excites me a lot is the machine translation. And the machine translation, it is supposed to be the AI complete problem and so on, but at the end of the day, it's a very straightforward problem. We have a sequence of source tokens, so that's going to be a source sentence, and then all we want to figure out is that what will be the translation of the source sequence. So machine translation system is going to take as input some source sentence, so that's Korean, and then what it's going to do is it's going to try to score every possible translation, for instance, in this case, English sentences, and then assign a high score to the correct translation. So pretty straightforward, except that there's a lot of English sentences from which we need to select the translation. In other words, we need to somehow build in some kind of structures into our model so that we can run the inference or the search procedure efficiently. So, like if we put some kind of restrictions on the structure, we can often solve these kind of problems really efficiently. If we assume that it's going to be a Markov model, then we can use the Viterbi algorithm, forward-backward algorithm. If you assume that, okay, this problem has a structure of tree-like structure, we can use some kind of belief propagation. And like even if not, we can use the approximate inference algorithm such as a variational inference, expectation propagation, loopy belief propagation, whatever. Let's say that there are like a bunch of books talking about all those things. But what we have noticed recently is that if we want to really build a good sequence model from which we can generate a realistic sequence, such as in the actual sentence, you make one mistake in translation, it just doesn't work. It just means completely different things. So we need to have a really good model of that. It turned out that a lot of assumptions that we make about especially the Markov assumptions, just break down everything. So what we want is we started to look at, okay, what is the way to build a sequence model that's without assuming much of the assumption at all. Actually, it's going to be the assumption-less model almost. So no Markovian assumption, nor the linear construction. This is great. It turned out that it works really well, except that the inference is really difficult, because the inference is effectively finding a relatively heavy needle in an exponentially large haystack, because we cannot really decompose this gigantic space into the multiple, let's say, chunk, and then do the search within it. We gotta, in fact, look at the entire sequences every time. Obviously, we know how to solve it up to a certain degree, and then today I'm going to go through, let's say, 3 different ways in which we can solve this problem. First one is going to be the monotonic sequential generation, which has become the de facto standard in machine translation as well as any kind of neural sequence generation model. The idea is that, okay, exponential space, not that great. We're going to decompose the problem into a series of next token prediction. So it's just like how we think, we speak. As in how we speak is to spit out one word at a time. So then, if I can do that perfectly, then all I need is a one classifier that's going to take as input whatever I have spoken so far, and then predict the next word. And I'm going to say that I'm going to use the same classifier to consume whatever I have spoken so far, and then predict the next one. And then just go on and go on. And then if the predictions were all perfect, then we recover the correct sequence perfectly in linear time. So that's great. And then, of course, then a lot of people will say, but the error is going to accumulate. How are you going to handle it? And so on. It turned out that it actually works pretty well. So all we needed to do was to ensure that we build a model such that each and every conditional is going to look at entire history of what has been generated. So, okay, let's try to use this. So in the case of the translation or speech recognition, it's all the same thing. So we have some input that's going to be consumed by the encoding neural network that's going to output some representation of input that's going to be more amenable for the decoder to consume. And then this decoding neural network, which could be recurrent neural nets, convolutional networks, or the self-attention network, is going to try to predict the first token, and then given that first token, trying to summarize what has been predicted, and then predict the second one, on and on and on. And then all we need to do is simply train this model to predict the next one given the correct one. And then that corresponds to maximizing log likelihood. And then nowadays, we actually know pretty well how to do that. I mean, like today, I saw that already even physicists are training all these deep neural networks. So not surprising that we, the actual deep learning people, know how to train these models really, really well. And we can use the LSTM, GRU, convolutional networks, memory networks, and then we can really train it well. And these days, we actually train these models on billions of the sentences, or sometimes even more. So the inference is a bit tricky because solving this problem turned out to be intractable. So what we do is that we are going to do approximate heuristic. That's what we know how to do well. Without knowing how well the problem is solved, we often solve the problem. So what we're going to do is we're going to select one symbol at a time. And then obviously that's very suboptimal because we don't really take into account the future consequences of the selection at every time step. And then we cannot really change the symbols that we have committed earlier. Then we can do a bit better by doing beam search. There is a reason why I'm moving a bit fast here because the exciting thing is at the latter half. So we can do a bit better by taking into account the multiple possible hypotheses. But obviously still the finite number of them. So it's still less suboptimal. It turned out that it works actually pretty well. And then we can continue to come up with the new heuristics to get slightly better every time without knowing where the limit is. So that's a bit unfortunate thing about this neural sequence model is that we think we know how to solve this problem and then we use it in practice. These models are in fact running on the phones you have. Actually, every one of them, especially if you have an Android, is running there offline. And still, we don't really know where the limit is. Some people say that some people tell me oh, that's really important. Some other people tell me that that's not really necessary. But we can always come up with a slightly better version over and over. So this iterative beam search algorithm is from the paper that I just wrote with my PhD student earlier this year. It works slightly, marginally better than just usual beam search. So are these models actually work? So as a case study, I decided to show that, okay, machine translation is too straightforward the problem these days. In fact, the same model can be used for modeling a dialogue or the conversation. So let's think about in this case. We want to build a bot that is able to look at who itself is and trying to make a conversation with the other bot. It turned out that this problem can be solved quite straightforwardly by using the very same technology, where we're going to say that our input is going to be the profile of myself and all the utterances so far. And then all we need to do is train this same model to predict the response. So what kind of response would you expect? And then what we need to do is, given the conversation so far, trying to decode out a response from this model. Now, biggest issue with this kind of structured output prediction and when we have humans in the loop is evaluation. We actually don't know how to evaluate them because it does require the actual interaction. So we ran the human evaluation using the Amazon Mechanical Turk, and then we did not tell the Turkers whether they are talking to bots or actual humans. And then we wanted to see if the Turkers can actually score these models better than humans. And then unlike many of the papers you see from the, let's say, OpenAI or DeepMind, humans were able to tell very, very clearly that they were not talking to humans. However, one thing we noticed was that in fact, all these things that somehow very heuristically we came up with, like the greedy decoding, beam search, iterative, so on, in fact, does make a lot of big differences when we look at the model performance, even though it's a human evaluation. So that's an interesting thing. Once you train a model, so these are results from a one model trained on the same data points. Then what we do is we're going to just change how we use the model. First, we can use iterative beam search. And then what we see is that even the humans were able to notice the difference across these different search algorithms. That's when I kind of realized that, okay, so perhaps the search and inference matters. And then what if we actually think about this more from the search perspective rather than from the modeling perspective? Then can we actually come up with the different ways to tackle this problem? So before moving toward this monotonic sequential generation, although I show you the very, very weak experimental results on the conversation model, it works really well. Search is still an issue in practice, in principle, but works really well. And then some people started to get scared about the, let's say, consequence of having this kind of left to right monotonic generation model. OpenAI decided that they have the so good a model that they cannot reveal it to the humanity. So that's unfortunate thing. But at the same time, you see how well it works. But then at this point, you start asking yourself. So what we looked at is the monotonic sequential generation. Can we then move this sequential thing? So we're still going to stick to the monotonic nature, but we're going to say that, okay, can we actually generate in parallel all those symbols? Instead of going left to right, one symbol at a time, we want to generate the entire thing. So just, at the, like this animation shows, we're going to start with some sequence that were generated all together simultaneously, and then we're going to iteratively find them little by little. Instead of trying to commit to one, and then commit to another, commit to next, and so on, but we're going to look at the entire sequence over and over. And another motivation is that most of the search issues actually comes from the fact that we stick to left-right sequential decoding. If we do the parallel decoding, can we actually avoid the issue with the search? And we go all the way back to 2006 and 2007, where people were working a lot on the layer-wise pre-training. So that's when we were calling this kind of network very, very deep. Then we had to try to train them layer-wise, and then stick them up, and then fine-tune. I also spent my PhD years on doing that. I did this one, and a lot of people at NYU, right, our neighbor, actually worked on this, and then spent, let's say, about 10 years on doing this, until Alex Krzyzewski realized in 2012 that you don't need any of this. However, we learned something from this. That is, in fact, how to capture the structure behind the data. One of the most effective ways is to learn to denoise. So when there is some kind of data, how we can figure out what is behind the data is, in fact, to denoise the data. And then if I can denoise it well, then I have captured what is underlying the observation. So in the case of restrictive Boltzmann machine, what we do is we start with the observation, and then we let the model corrupt it by running the Gibbs sampling chain, and then eventually the statistics we get from this corrupted version should match the original data. So that's how we train the restrictive Boltzmann machine, and that's how this restrictive Boltzmann machine learns the density behind the data. Same thing with the sparse coding. We start with the data. We're going to estimate the first sparse code, and then we're going to iteratively apply the shrinkage operator, and then from there we try to reconstruct the original version. And we say that the sparse coding, or this kind of iterative sparse coding mechanism, has learned something about the data when we say it can actually recover the original data as well as possible from this sparse code. Denoising autoencoder goes a bit further, saying that all right, so then do we actually need to let the model corrupt the data? We're going to simply build our own corruption process and then train a denoising function to reconstruct the original one after feeding the original data through the corruption process. It turned out that the denoising autoencoders do the exactly same thing as the restrictive Boltzmann machines, as well as the sparse coding, with a lot of assumptions that make them look similar. But at the end of the day, what it learns is some kind of vector build. And then whenever you start from anywhere that is anywhere near the data manifold, then just following these gradients will bring the point toward the nearest data point. So that's what denoising autoencoder, restrictive Boltzmann machines, sparse coding, all of them learn to do so. Then one obvious direction that we should follow is that, okay, what if all these points were sentences? So this manifold is where the correct translation lies. All the other points are slightly incorrect translations. Then what we can do is we can actually train this kind of denoising autoencoder to do the translation or the sequence generation. By starting from some random sentence, we're going to let this model denoise it little by little until it goes to one of the nearest point on the data manifold. So what we do is we start with the source, x. We again encode it into some kind of representation using an encoder. We introduce a corruption process. Largely, it turned out that all we need to do is some kind of local corruption. We're going to swap some of the words, drop some of the words, or we're going to leave the words as they are. And then train this decoder to simply reconstruct the original sentence, starting from this corrupted version. Then in 2014, Yashua Benjo told me that we should do this, and I completely ignored him. Turned out that it actually works. And then in about 3 weeks, I believe we're going to have a much better version. 3 weeks and 1 day, was it? Yes, 3 days and 1 day, we're going to have a much better version. So at the end of the day, the model we end up with for sequence does not have much of a sequential structure anymore. What we do is this model is going to generate the entire sequence altogether and then trying to fix it little by little. It can be trained using both the denoising as well as to end-to-end backpropagation type of algorithm, although it turned out that denoising is the most important component of this learning. And inference is trivial. All we need to do is we just run it through this network over and over. And then as you can see on the plot left to it, even though the model was trained with a fixed number of refinement steps, as we refine it more and more, the score gets better and better. That's true all the way up to 100 refinement steps. And then the model was trained only with the 4 refinement steps. So this kind of denoising really does learn how to refine it and then learns to stop when it gets to a good point or learns close enough to the data manifold. So let's look at some examples. I don't know if anybody speaks German, so source is German, and then target is English. This is not a great translation, I have heard. So initially, it's going to generate some sentence that syntactically is roughly gibberish, but has a lot of content words. But then model is going to refine it further and further. As it refines, you do see that the sentence gets better and better formed, and then the contents also get more and more correct. And then this is not even a cherry-picked example because that's how we train this model to capture the underlying regularity in these sequences. Any example, any sentence you give as a source is going to translate in this kind of, let's say, refinement, oriented way. And then that works for image captioning as well. So given this image of a Amtrak bus parked in a parking lot, the initial version is going to say a yellow bus parked in of parking lot road. So it has most of the content, but it really doesn't make sense of what the syntax should be. But by refining further and further, it actually adds in a bit more content and also make the sentence much better formed. So it turned out that late last year, we learned that the parallel decoding is a viable alternative to sequential decoding. And then really so, it actually was realized by the multiple groups simultaneously. Salesforce AI Research, DeepMind, I think. Yeah, DeepMind, and then another group, Wang et al. They all show that this kind of parallel decoding is possible, all simultaneous around the time of summer last year. And then it turned out that all these, let's say, generative models are very necessary for the structure prediction. Okay, so far so good. I still have some time, right? Yeah, like 10 minutes. That's perfect, actually. 5, okay. But that's perfect. So we talked about sequential. We tried to remove the sequential. Then what if I keep the sequential, but if I could remove this monotonic assumption. So instead of trying to follow the structure of the surface that is left to right or the right to left one at a time, can we actually build a system that's going to generate symbols in arbitrary order? And then later, when you look back, you see that they are actually forming a very well-formed sentence. That is, instead of trying to follow whatever the data is telling us to follow, can our model discover what were the underlying mechanism by which that sentence was generated? Turned out that the answer is obviously yes, but let me show you what I mean by it. So when we look at the data, let's say the sequence data, what we would think is that, okay, this is a sequence of different symbols, the cassette on the map. Another way to look at it is that the sequence is really a combination of a multi-set of items that you need to predict and the constraints on how they should be placed. So in the case of the sequence, we have a full constraint, quadratic number of them. So the has to appear before every other word. Can needs to appear before every other word except for the. Said the same thing and the on the way. And then what is telling us is that if we could use this view of sequence generation, what it means is that we can generalize the sequence generation in a way that we are going to predict a set of items with some set of constraints that are not necessarily complete. So then, what we start with is that what if the constraint set is empty? Can we do that first? It turned out that we didn't actually know how to do that. So set prediction turned out to be an extremely difficult problem that no one had a practical solution until very recently. I still don't understand how that's the case because set prediction actually does have amazing application. That's really important for Instagram, Twitter, and so on, but somehow we never really had a good solution to that. We had a solution to predict whether each set should appear or not independently of all the other sets. But to model all the dependencies among the output items, that has not been really studied that carefully, or at least not in a practical sense. So we started working with the multi-step prediction, where we say that, okay, we don't have any constraints. Let's try to learn to predict all those items in a set while also capturing the strong dependency among them. So this is what everyone was doing. That is, for every possible item, we're going to see how many of them should appear, regardless of how many other items should appear. So instead, what we want is that if we want to use this kind of sequential generation model that knows how to capture all these dependencies really, really well, to generate a set that's going to be as similar as possible to the ground truth set. And we were inspired by the Benny Uria, who is now at DeepMind, on his PhD work on the DeepNate, where he showed that you can actually train a autoregressive model like the pixel CNN without having order. So you can actually train it to be agnostic to the ordering of all those pixels. That one really didn't work out well, I think because of the naming. They should have called it PixelNate. I'm pretty sure that would have taken off because it's exactly like Pixel CNN, but with a better way of training it. So I'll just skip this since I don't have really time. So let's look at this. This is actually the essence of the whole, let's say, multi-step prediction. Given some input, we're going to let this model predict the items that's going to show up for a few steps. And then what you notice is that given that, you have the predicted set of items, and then you have the ground truth set of items, at the union as well as the intersection. And then given this predicted set of items, what we can look at is the complement of the, let's say, ground truth items after removing all those the predicted items. And what we can do is, given this valid set of items, we can compute the loss with respect to the new prediction. So in other words, usually what we do is that, okay, what is the correct item that needs to appear at, let's say, time step 3? What we are saying is that what are the things that could be appear at time step 3 instead? And then in the case of the multi-set prediction, because we don't have any constraints, so anything that has not been predicted so far can appear there. However, as you have more and more constraints, you can now construct a more sophisticated or complicated a set of valid items. They are going to only satisfy all the constraints that you have. In the case of sequence generation, it turned out that the quicksort, if you remember from the, let's say, algorithm 101 or so on, is extremely nice way to build such a valid set at every time step. So we're going to build some kind of policy that's going to tell us at every time step what are the valid items to predict. Does anybody remember actually how quicksort looks like? Other than just using the numpy.sort, right? So how it's implemented on the line. So at the very beginning, at the top, we can predict any one of these items in order to get to this eventually. Let's say I decided that, okay, I predicted on. Once I have on works as a pivot item in this initial set, and then splits the sentence into dog, set, cat, and mat period dog. Again, the order doesn't really matter. So that was a time step 1. In time step 2, now I can predict any one of the set, cat. Let's say I selected the set. And then time step 3, I know what can be predicted. That is mat period dog, one of them. Let's say I predicted mat. And then I can do it over and over. And whenever I have the empty set, I'm going to just put the stop symbol. And then once everything has stopped, what I can do is I can do so-called, so this was the order of generation, level set traversal. Now what I can do is I can do the in-order traversal in order to recover the original sentence. This is how quicksort works. So we start with some unsorted sequence, find one pivot point, split it out, find another pivot point, split it out, and then at the very end, you do the sorting of the two numbers, and then now you do the in-order traversal. Suddenly you have the magically a sorted sequence, and then it turned out that we can use this for training this sequential generator because all we need to do is train a neural net to follow this order. Then every time, at every point, all we need to do is tell the neural net that you can predict any. So we don't really tell the neural net what to predict. We are telling, in fact, the neural net what it should not predict at all. Otherwise, it's free to do whatever it wants. So let's look at how we are going to train. So we're going to let this neural net decide what to generate. And then at some point, we're going to say, okay, so we have a set of valid items. So let's compute the distribution that we want to impose. And then let's ask the neural net to match this distribution. Simply use a KL divergence. All right, so anyway, I'll show you some result examples. That's because that's the fun part. So then when we train this kind of sentence generator model, this is an implicit graphical model as well, probabilistic model, because it doesn't really give us the correct valid probability. So this is how the sentence is actually generated from this model when we train it on just sentences. Start with a period, you, period, I study, I stop, stop wish, could LOL, stop all, stop, 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 stop. So everything has stopped. And then now you do the work lot, stop, 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 stop. You do the in-order traversal. And the sentence you get is, I wish you could study LOL, period. I work a lot, period. And then this is how the model is in fact generating. This is how we interpret what model has generated. And then, we can do all these things, like, okay, the time's up, but this is like another example of translation. So how would we read this? So this is the order of generation. Cool, how, but, never, I, been, like, and so on. But it's in fact saying that the how I would like to, how cool, I would like to, but I have never been outside of Ohio. So it's learning all these orders without being told in which order the sentence should be generated. And then it actually learns the orders that corresponds to our knowledge about how the sentences are in fact processed in general. All these things. And then at the same time, there are similar paper from the Google, Facebook, and DeepMind all together within about 2 weeks of the time. I don't know how that happens. But at the end of the day, I think the really interesting thing is that when I have this kind of model that generates a sentence in an order that is completely learned, then what is that order it has learned? So if you train this kind of model on the physics observations that you have, and then suddenly it learned to generate all those observations in an order that you never told the model to do so, then is that order a physical law, maybe physics law, or something like this? So, and thank you. That's it. Sorry, I took too much time. Mhm.
I'm just curious about the order that it does actually make the predictions. Does it use like a dependency parse
So yes,
or
so
something like that?
what is the actual order? Yeah. So we have done some let's say analysis. This is the predicted order where this is going to the depth of the tree.
Oh, I see. Yeah.
And then this is the type of the words, like is it punctuation, pronoun, noun, verb, and then this is what you get from the dependency parse. So what we see is that except for the punctuation, because in dependency parse we largely ignore the punctuation, verb almost always starts earlier, and then pronoun always comes earlier than noun. So we do see some kind of correspondence. And then another interesting thing is that this is the normalized entropy over time of generation. So the usual left to right, you start with a very high entropy because you cannot tell what should be done. And then as you generate, you accumulate the evidence, so the entropy goes down naturally. But in the case of this annealed one, which is the proposed one, the model starts with the most confident one and then goes down by predicting the less confident ones. So that's why it starts with the punctuation, because almost every sentence starts with has the punctuation, and then goes to pronoun, and then given the pronoun, it goes to one of the nouns that could be any one of the potential nouns for that specific pronoun. So it does have a very, very different way of generation. Yes.
Some ideas of reinforcement learning in the sense that you're teaching what not to information, or just sort of reinforce. I don't know if it makes sense.
Right, right. It does make sense. So in a sense that the one way to view the reinforcement learning is that you run your policy for some time, and then from there on, you want to figure out which one of the actions are good actions. So one naive way is that you're going to just try out all possible actions from there on, and then look at what kind of return you get, and then trying to do the classification, right? So trying to learn that correct action. And then that actually bridges the notion between the reinforcement learning and then learning to search for the imitation learning. So what we do is closer to imitation learning, where we have access to an oracle that actually tells us what is the correct thing to do in terms of distribution rather than a single point. So the single point would be the RL type of thing, yes. Mm-hmm. Right. So yes, so the grammar or the syntax in the linguistics probably is closest to physics, but my belief is that the linguistic syntax or even the semantics far, far from the, let's say, the confirmedness of the physical law. Yeah, let's put it like that. Yes, but what we see is that this dependency is actually the result from the dependency parse. That is one of the shallow parsing methodologies. And then what we see is that we do see some similarities between what we have, what our model has recovered versus what the usual dependency parse framework tells us. So in a sense that we do see some, let's say, analogies here and there, but nothing too concrete. That's just because the syntax theory is not that actually concrete to start with. There's no linguist here, right? Computational linguist? No? Okay, that's great. Okay, okay, good, good. I think the physics law is much better. Okay.
Stuff generalized to other NLP tasks?
No, we haven't looked at it. We are looking at actually generalizing this idea into the graphs at the moment. So when we try to generate a graph, so one of the a few dominant approaches at the moment include, let's say, first one is that you just try to generate the entire affinity matrix as if they were image, right? So you can do that. Or the other one is that you're going to generate it, do the matching, and then trying to reinforce the model so that it's going to generate as well as possible. Now, if we generalize this quicksort, then we can actually generalize this to the entire graph. And then one of the problems in NLP is to predict the graph-like parse on the sentence. Like those are mostly semantic, let's say, parses. There we are looking at what is the right way to build this kind of quicksort, like let's say Oracle on that. Limited research. We still have 3 weeks and 2 days actually for the natural language processing conference, EMNLP. The deadline is right after the deadline of the NeurIP. We'll see.
So there's sequences, there's graphs, but then there's also like trees specifically. There it seems like the order might be a little bit more clear. Have you thought about that?
Right. So trees, we were actually looking at the trees, but we decided to look at the graphs because trees are a bit really difficult to find the direct application of right away if you want to do this. Graphs are much more prevalent. So in the case of the tree, what would happen is that they will have to make a decision about whether we are going to build the Oracle policy following the breadth first search or the depth first search. Now, I believe this approach is heavily dependent on your design of the Oracle policy. So that's going to be very interesting to see, what is the better way to go. Oh, okay. Looking forward to that. We got to work again. Yes. Thank you.